Are you able to hear my voice? Let me just checking. Are you able to see the screen?
Yeah.
Okay, great. Thank you. So um, today we change our topic. So the topic will begin the number base in a different number. So we have been working with all the from chapter 1 all the way to chapter 7. We assuming it's actually decimal system, and which we used to be. Right now, we consider other number system. So why do we study other number system? Because it's just quite useful. For example, like computer, if you use computer, you use binary system or you use octal system, or you may use the hexadecimal system. And if you use the internet websites, and maybe you actually, if you use the bullet point, then you're actually using like 26 system, base 26. And if you use like time, you actually use base 60 system, because second, minute, hour, so actually, it's rounding at every 60. So there are applications that used in everywhere that use other number systems. So let's get started on what that is. And so why do we use like decimal system? Is actually, it's just fairly simple. We happen to have like 10 fingers. And so the word digit, is just finger. So basically, if you looking for so using 10 digits, so 10 fingers, basically. And because we have 10 fingers, that's why we use the decimal system, which, we round up at every 10. And then this is just ancient, this is the ancient Egyptian counting system. Like, every 10, it became a arch. Every 10 arch, it became look like a sprout. Every 10 sprout became a flower. And then every 10 flower became like a finger. Then every 10 finger looks like became a sheep or maybe a dog. Then every 10 dog became like a queen. So this is actually 1 million. So basically, you actually rounding up at every 10. So that's a very common. So the most used number system is the base 10. So we kind of see, how to count those number of the digits, or how to count those points. This is actually very hard to count. But if we rearrange those points into like every 5 row, so 1, 2, 3, 4, 5, so have one row, one column has 5. So we skip counting 5, 10, 15, so kind of much faster. Then if we do more grouping, this one, this is a 5 to row, then this is 5 by 5. So this is 25, 25, 25. So we got 75. Then this is 10, this is 3. So that's much easy. That's going to be 88 if you add them together. So basically, Zia, why do we invent the number system at all? It's just for the convenience of counting big numbers. Otherwise, we would spend all day just counting and not even getting any result. So what's the trick of the decimal system? So this decimal system is basically bundling. So for every 10 stick, we make a bundle. So this is just basically wraps them up with a band. Then every 10 bundle of 10 straws, we get a bigger bundle. Then for every 10 bigger bundle, this is 100. For every bigger 100 bundle, we can make a full box, a package of 1,000. So basically, that way we actually is able to count things much faster. And in this number system is actually position value system. So basically, for example, 3572, actually, though they are all together, for example, decimal system has all the digits. Possible use digit is actually 10. So that's why it's called decimal. And those starting from 0, 1, all the way to 9. So those digits could appear on any position, and its meaning will be different. Even 0 appear on 100 position means just, it's a position holder, that meaning that it's 0 hundreds, and it's still a little bit different from a 0 that in a lower digit position. So basically, it became a position value system. For example, 3 at 1,000, it's actually corresponding to 3 huge boxes of straws. Then 5 on the 100 position is related to 5 big bundles of straw. Then 7 at the 10th position corresponding to 7 small bundle of straw. Then 2 at the 1st position, just 2 straw by itself. So basically, this is kind of using the digit bundles to make it convenient and accurate. So this is actually so this is the expanded exponential form. So each position value actually corresponding to 10 to the m's power, n is the position value where it stays. For example, like 1,000 because there are 3 positions to the right of it, so it's actually 10 to the 3rd power. So that's the way that position value use the exponent and combined with addition is able to reuse the digit on every position value system, and you can use very few possible digit to count up to infinity. And also you can after the decimal, it can count down to the infinitesimal. So basically that's kind of the digit system we are dealing with, but normally it's base 10. So right now we are trying to deal with other base. For example, like how about we do like 3 base? So if we do 3 base, it will be just a little bit different. And this is basically the 5 base. If we, the bundle size, the straw little bundle size is not 10, it's 5. So this is this is actually, you can rewrite this model into a base 5 system, which going to be 3, 2, 3, and subscript 5. Subscript just is a base 5 value. And so it just means that, it's equal to 3 times 5 square plus 2 times 5 plus 3. So basically, this is just, we borrow the idea of position value in the decimal system and propagate it to other like different bundle size. We can create other different number-based system. So that's the way we do it. And so basically, the base number system could be using a different value. And normally we use base 10, but it doesn't has to be base 10. For example, this one is base 3, and this one is base 3. So what is difference between different base? And 3 basically, you only have 3 digits to rotate. In a 3 number, it's a base 3 system, you only have 0, 1, 2. You cannot have 3 because 3 is where you bundle, you rounding up. Like decimal system, you don't have a digit for 10. In order to represent 10, you need 2 digits. It's 1, 0. And that's so the base number system, when you mention it, it always starts from 0 all the way to the number, the base set you -1. For example, a base 3 system, all the possible digits start from 0 and 1, 2. Count them together, that's 3 position. So 3 possible value. Because you're counting from 0, that's why it's always 1 short on the top side. So because this one, like, the quantity, like 5 multiply 3 square, you cannot say that it's 500 for the 3 because 5 is not allowed digit. So you basically, actually have to represent it with other things. So 5 is actually equal to 3 plus 2. So basically 3 is where you round up. So basically it's actually 1, 2. So 1, 2, 0, 0 is actually the way to represent, 5 multiply 3 square in the 3 decimal system. And it's not 3 decimal, it's just a number 3 system. And the base number, basically, it has a lot of different ways saying it. And so basically the way we say it is that if you have is base 2, it's called binary. And if you have base 3, it's called, if it is base 3, it's called ternary. If it's base 4, it's called quaternary. Then it has so many different names. And you may not have, so these are like computer preferred hexadecimal, like, this is octal and binary. And so then this is the human being most preferred one, the digitals. So those are normally used actually in your life will be, then this is like using time, sexagesimal. And so these are commonly used, you actually not, others are more find in your like math problem. So how do we deal with the number? So let's say that few in 0, 1, 2, 3 to make a true statement. So basically right now we are just trying to express those numbers. So these are decimal number. If a number without subindex, without subscript, this is a decimal system. Then we're trying to express into this is like basic system. Basic system, you can only have 0, 1, 2, 3, 4, 5 digits. And then here, basically, this is like, this is basically 36. This is 4 multiply 6 is 24. So this add up to the 60. Then we have 3. So this is 3. So if you're trying to fill those in, this is actually fairly simple. We need 60 plus 4. So this is still the same, 1, 4. And that's going to be 4. Because we are allowed to increase 4 to 4. Then this is 1, 4. 5. Then up to here, we will be totally different because 5 is where it's rounding up. So basically, when we round up 5, it's going to be 150 because it's just like, you're counting the decimals. When you count to 9, the next one you're going to zeros and rounding up the next value by 1. So this is rounding up effect. Then we actually we will stable for a while. Then we can, this is 1, 2, 3, 4, 5. So here we actually can just copy down 1, 5, 1, 5, 1, 5, 1, 5, and 1, 5. Then here is 1. It's going to rounding up in a bigger way. Basically, 5, you're adding 1, it's going to become 0. Then rounding up, you already up to the 5. 5 plus 1 going to be 0 again. And this is basically is 1. Rounding up, so there's extra 1 here. 1 plus 1 equals 2. So this is actually quite easy to understand because 72 is actually 2 multiply 36 square. So basically it's actually, 6 square. 2 multiply 6 square. So 6 square basically in terms of the centenary system. So centenary is for the 6. For the centenary system, basically 1006 is actually equal to 1 multiply 6 square, just as if it is a decimal system. Base 10 is actually 1 multiply 10 square. So whatever the number you use as a base need to be always present in the power expansion form. So this you then you reach a new stable state. You can just rotate 1 and 2, then going up. So this is just showing you the way that counting in a different number system. It's very similar to the decimal system. It's just reaching the upper limit of the available digit. It's going to round up. Then sometimes, for example, this is at 155. 5 is the last digit for the centenary system. Then basically, when you add 1, it has a cascading rounding up. So that's the way that you do those. You kind of do those calculation and those additions. And then we also have, make a list of 64 smallest positive integers that can be written using only 0 through 7 inclusive. What will be the last number you list? So basically, we need to make the 64 smallest positive integer. We're using only 0 to 7. So basically, we are not allowed. So basically, this just look like positive integer. So positive integer. So this actually, we are still counting the decimal system. So it's not mentioning the like 0 through 7. 0 through 7 basically is the octal system because 0 to 7 they are a digit. So you are only allowed to use a digit to express things as you're counting up. So what would be the last number in your list? Then basically this is actually equivalent to counting up using the octal system, because in the octal system you are not allowed to use 8 and 9. So basically, whatever whatever decimal number you are using actually has one-to-one relationship. For example, 1 to the eighth, a base is 1 to the 10 base. Basically, you can actually build a one-to-one relationship this way. So basically, then if we count by the octal system, basically, if we count up all the way for 64 numbers, 64 smallest number count by, it's actually 8 square. So 1 multiply 8 square is actually equal to 100 in the number 8 in the octal system. So basically, the last number in your list, even in decimal, it's going to be 100 because actually the rounding rule, because you take away two number, the rounding rule in decimal still looks exactly as the octal rounding rule. It's just one-to-one mapping and what you are having with. So this is one kind of the interesting problem. And so solution for this one, basically, how do we write decimal so here basically it's already using so it's actually using different number. So the problem showing the light blue and the problem showing the dark blue actually are totally different, but they are equivalent. So basically, we basically, this is counting without a 9, basically equivalent to the octal digit. So the last number in your list basically is 1008. So basically, last number we have actually in the decimal is 100. In the octal is still 100 to the 8th, and that altogether there are 64 number altogether. So that is the way we analyze this type of the problem. Then let's trying to get to the different number-based digit. So the different number-based digits, so we already showed this, is that for anything below 10, that's actually easy. Below 10 decimal, basically you're just cutting out numbers. For example, if I'm doing a 7 base system, so I rotate from 0, 1, 2, all the way to 6 using 6 digits. How about 11 and 12? So right now it's giving you an example of like base 12 system. So after we running our digit, basically, our convention is that we replace it with the Latin letter, English letter. So at 10, we began to use A or use alpha, Greek alpha, that's okay. Then 11, basically we use B, or we can use beta. So basically that actually will make up our, base 12 system. So the way we count is as 1, 2, 3, 4, 5, 6, 7, 8, 9, alpha, beta, 1, 0. It's not really 10, basically it's 1, 0 in the 12 base system. Then this is 1, 1 base 12. So then that's 1 alpha, 1 beta, something like that. Then, before 1, 0, 0, it's double beta. So basically that's the way and here, even for the same book, it's actually sometimes using Greek letter, sometimes it's using the English letter. So basically, you know, both of them actually is okay. It's interchangeable. And so, you know, given 26 letter, you actually is able to express all the way to like 36 digit. So basically, that's actually, you know, quite convenient. You can express base 36 system. And so this is the you know, hexadecimal. Hexadecimal is extensively used in the internet. Like, you know, the way, for example, this web page is presented, it may using the RGB color. RGB color, so usually they will use like 6-digit hexadecimal. For example, you know, yeah. So let me just show the like they actually has a lot of W3 school, and W3 school has a lot of nice computer related thing. For example, HTML color. HTML color, so there are a lot of ways they have color name, and they also have like RGB color. RGB color basically is base 16. You can express in the base 10 number all the way to 255, but there are other ways that using the hexad number. And let's see. Yeah, this is a hexad number. Let me show. I just saw it. So this is the hexad number. So pound FF63 and 47. This actually is equivalent, believe it or not. So basically, you know, if we try it, these color basically, you know, 255 is FF, 63 in hexadecimal is actually 99, and 47 in hexadecimal is 1771. So basically, those actually the same color, and that's the way that, you know, you actually can see a whole lot of hexadecimal things, and if you do the computer work. And so hexadecimal, how it works. So basically, hexadecimal is 16 base. 16 base, you are missing 6 digit, 6 letter, or because 10 base, you 0 all the way to 9, then 10 is A, 11 is B. So this is 10, 11, and 12 is C. And then 13 is D, and 14 is E, and 15 is F. You know, so for example, just as this system, this is a color which, you know, FF is related to 255 because in hexadecimal, it's just 15 multiply, F is 15. 15 multiply 16 to the first power plus 15 multiply 16 to the 0 power. This is just 15. This is basically 240. And then you add it together, it's kind of 250. So basically, you know, hexadecimal is very popular. It's often used to program color graph in computer. I just showed a case that, you know, where it's really being used. And you can actually adjust those hexadecimal value to change the color. For example, we can test this. And so for example, if I change this to 1, 2, then there's going to be a different color because actually change there will be less red, so there are more green and the blue. So it's more greenish and bluish. So, so that's the way that it's being expressed in a whole lot of cases in the computer. Then we actually this. So up until right now, it's actually very easy saying. So right now we began heading into the problem of really doing the conversion heavy duty work. So let's trying to see how those work need to be done. So write as sum of base 9-digit bundle. So this is just using the power expansion. So this is actually 5 multiply 9, because that's the 100 position. So 9 square plus this is 1 multiply 9 to the first plus 4 multiply 9 to the 0. So everything will be the same as the power expansion, power position value expansion of the decimal system, except the base of the power will be different. In decimal system, the base of the power is 10. In a different base, it's just a different number. Then to find the decimal value, you kind of just have to calculate it. So this is 5 multiply 81 plus 1 multiply 9. 1 multiply 9 is just 9. And 4 multiply 1 equals just 4. So here, 405 plus this is 13. So this is going to be 418. So that's the way that you can do this type of the problem. And let me check my answer actually is right. So basically, it's just replace the 9, replace 10 with 9. So you basically, you using the same position value, power expansion, you finding the decimal system, you will be able to convert a number in other base into a decimal number. So this one became I think let's increase some class participation. And Eddie, could you try to read this problem 8.6?
Okay. Group 65 marbles into as many piles of 3 as possible. How many piles do you have and how many marbles are left over? Group as many piles of 3 to the power 1 from part A into as many piles of 3 squared as possible. How many piles of each size do you have now and how many marbles are left over? Group as many of the piles 3 squared from part B into as many piles of 3 cubed as possible. How many piles of each size do you have now and how many marbles are left over? Write 65 as a base 3 numeral.
Okay, so this problem is very important. So we put a star on it. This is just, there are 2 ways to convert other base system into, this is I'm converting a decimal number to other base. So there are multiple ways to convert it. This is one of the way. This is called, continued division. Take the remainder as the position value each time. So basically, this is, let's see how do we do it. So 65 marble basically divide by 3. We're going to get 1, 2, that's 6. And then this is 1. We got 5 minus 3 equals 2. So remainder going to be 2. So as a base 3 numeral, you know, the ones will have a 2. I say this with very much certainty because imagine that if you already have a base 3 number, if you have a base 3 number, basically, you know, other than the last digit, these are all, any position here is actually, you know, this is 3 multiply, you know, this is 3 multiply whatever digit. Let's say that this digit is this is on the 10th digit. So T, 3 multiply T, and this is actually the 300 digit. And so basically this is going to be 3 square multiply H. And this is the 1000. So basically, you know, 3 cube multiply TH. So basically, you know, but anyway, every position above the unit digit always has a 3 multiple. So everything will be multiple of 3. So, you know, whatever left on the unit digit going to be the remainder of division caused by dividing 3. So basically, when you do this step, when you do the first division, basically the remainder will goes to the unit digit of the base 3 numerals you're going to calculate. Then after you did that, basically you get this 21. What does this 21 mean? This 21 just means that I have 21 3 bundles. Basically, if we are counting straws. And so this is a bundle. So I have 21 3 bundle plus 2 left. So I'm going to repeatedly divide it. 21 divided by 3, we got 7. So what does this mean? Because 21 is, you know, the quotient, but when dividing 65 by 3, then you divide 21 again. So divide by 20 or divide by 3 again. So we actually, you know, imagine it's actually bundle 3 bundle together. I'm trying to find how many bundle or 9 straw bundle, bigger bundle can I create with 21 small bundles. And actually I can, this is actually, I can get 7 because 7 multiply 9 equals to 21 multiply 3. So basically I can create 7 of bundle 9 with the 21 3 bundle. So given that fact, and also I have no remainder. So basically that actually means that on the 3 position, this is 3 to the 0, this is 3 to the first. So they are now left over 3 bundle here. So basically it's just 0 because the remainder of dividing 21 by 3 quotient is 7 and evenly divided. So the 0 goes to the 3 to the first position. Then we're going to repeatedly divide 7 by 3 again. So right now I have 7 9 bundle, 9 straw bundle, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's one of those. And I have 7 of those things. And divide by 3, what does it mean? Because right now I'm creating a bigger bundle, huge bundle with 27 straw, which is 3 to the cube, and to see how many of those bundle can I create. So 2 multiply 3 equals to 6 and 1. So basically, this just means I can get 2 of the 3 cube bundle, which is 27. 3 multiplied 27 equal to 54. And then we have one remainder. One is just I have a one left over of 9 straw bundle. So basically 54 plus 9. So this is actually, you know, one goes here, 3 cube or 3 square, that's 1. And then the last is actually 2, because quotient is 2. This is basically 3 cube 2. So basically we actually successfully convert 64 into base 3 by just division, repeatedly divide by 3. First, we get the unit position value as the first division remainder. Then we divide it again. Then that's the number 3. 3 straw bundle could be left over if we keep the possibility of bundling up higher. So that we have the 0 of those because we actually can evenly divide 21 by 3. Then the quotient of 7, we keep dividing that again. And 7 of the 9 straw bundle could create 2 of the 27 straw bundle with 1 9 straw bundle left over. So basically that is the idea of keep repeatedly dividing, and you start from the lower remainder and goes up high. So that's the first way of doing the decimal number to other base conversion. This is a very systematic way, very good. And then let's investigate the second way. So this is not the only way, there are 2 ways. So this way basically is bottom up. And this is bottom up. And then there's also top down. So top down, so these 2 problems are very classic problems. You actually need to really practice those and remember how to do it, because in AMC, and different number-based conversion is a heavily tested topic. So you actually have to truly understand it. So right now, I am trying to convert decimal number of 857 into a 7-based number. How would I do it? So obviously, let me just practice the previous method, just use the just learned method, try to do it. Then I'm going to use the new method, try to compare both, okay? So given we just learned method is 857 divided by 7. So we just repeatedly divide it, and that's 1 is 7, and 15, that's going to be 2 multiplied 7, 14, and that's 17. That's going to be 2. So that's 14. Remainder is 3. So 3 goes to the unit digit, 7 to the 0. Then the quotient is 1 to 2. We divide by 7 again. So that's going to be 1 multiplied 7 equals 7, and we got 5 remainder, and the 2 copy down, and the 7 multiplied 7, 49, and we have 3. 3 again as that's on the 7 to the first position. Then we have 17. 17 divided by 7, and we got 2 multiplied 7 equal to 14, and 3. 3 as remainder. So that's going to be 7 to the 7 square. And that's going to be that's 3. Then we have 7 cube. 7 cube is where this goes. So basically this is going to be 2, 3, 3, 3 as 7 base number. So I'm going to change the color pen, trying to trying to investigate this conversion, number conversion at different angle. So first we trying to see, how many digits from top we actually need to achieve this. So 7 to the 0, we just try to gauge the size of 7 power. So the 7 power, 7 to the 0, that's 1. 7 to the first is 7. 7 square is 49. And 7 cube is basically 343. And then we also need to get 7 to the 4th. 7 to the 4th basically is 49 square, which is 50 minus 1 square, which is equal to 500 minus 2ab minus 100 plus 1. So basically it's actually 2401. So 2401 obviously is way bigger than 857. So I don't need that many digits. So the top digit I'm going to use is 7 cube. So 343. So I can divide. Let me change a color. So 700 or 800 and 857 divided by 343. I can put a 2 on it. So 2 multiply 3 equal to 6. 2 multiply 4 equal to 8. 2 multiply 3 again equal to 6. So this is 1, 7, and the 1. 171 is the remainder. So 17, so basically this is actually exact top-down position. So we know the highest digit we can use is 7 to the 3rd, and we already get quotient 2. So quotient 2 goes here. So we actually, quotient 2 goes here. Then 171 and 171 divided by 7, 49, because the next one, how many 49 straw bundle can we get out of 171? So 49, we can get out of 3. So 147. So that's going to be minus, going to be 4. And this 6 minus 4 equals 2. So 24 is the leftover, but basically quotient is 3. So under like 7 square, because you divide by 49. On the 7 square position, we get 3 as quotient. So that's 3 value here. The leftover is 24. 24 divided by 7, because the next position value is 7. And 3 multiply 7 equal to 21, and remainder is 3. So this quotient goes to 7, because we have 3 of the 7 straw bundle. So that's 3. And remainder is 3. Remainder is 3. So basically, in both ways, we actually reach the same result. So basically, there are 2 ways. Personally speaking, I prefer the first way. I use the second way for double check, because first way, you kind of just keep dividing it. You keep only dividing one digit number repeatedly. You always get it right. And you can notice you have much higher calculation volume by going the second method, because you need to calculate the position value size on each power position. Then when you do division, you're actually dividing big numbers. For example, you are dividing like, a 4-digit number by a 3-digit number in the first attempt. And the second attempt, you actually divide a 3-digit number by 2-digit numbers, and later on it becomes smaller and smaller. Imagine you are dealing with a like a very big number, for example, 10 billion number or 100 trillion, then the first method obviously is very consistent, very easy. And this method, I think you will get it really difficult, just create a lot of problem. So those are highlights that definitely you need to master and definitely need to practice a bunch, need to know. And the second problem, the second method has a advantage is that you know the ballpark size in a new number system much quicker. So basically, when you power them up, 1, 7, 49, 343, and 2401, you know that 857 land between those. So basically, you know the top digit is the 4th digit. And then you also know that you can fit 2 of those in. So basically, the first digit is 2. So basically, that actually, and if you start from tail up, especially if you make calculation error, your higher digit likely will be wrong. And here, this method could help to double check and correct your problem if you looking the problem from a different angle. So I think I'm getting feeling messy here. So let me just do another page. And so this one basically is trying to convert 204 6 base to 10 base. And then we need to convert this answer from this 8 to the 5 base. So let's using like 2 minutes trying to convert this to see if everyone getting the idea about different base conversion. So we're going to wait until 7:31 to see if anyone is able to. And basically you have to use the position value system. So basically 2 multiply whatever, and 0 need to multiply whatever, and then 4 need to multiply whatever. So basically think in this direction and see if you can get the answer. Let's see. Let's see if anyone, actually time arrived. Looks like no one, oh, someone getting the answer. Let me see. isn't just 76. I don't really know. Let me try to do it. And so this is actually, this is going to be 2 multiplied because this is on the 100 position. It's going to be 6 to the square. Then this is going to be plus 0 multiply 6 to the first. Then plus 4 multiply 6 to the 0. So that's the way you do the conversion. And this one basically is the 72. And this is plus 0 plus 4 equal to 76. So yeah, you're right. Looks like Xinlai got the problem right. Very good, very good. So then the next problem is try to convert your answer from A to base 5. So basically, you know, your basic system is a 76. How to convert to base 6 or base 5? Convert to base 5, basically you already get a decimal, so you need to convert this decimal into the base 5. And so there are like 2 different ways. And I also can throw in a third way. So let's take 2 minutes, try to do this problem again. And part B, try to do the part B. My hint for part B, you can repeatedly divide by 5. 76 repeatedly divide by 5, or you can use less order 5 power, then try to gauge. One is repeatedly divide by 5.
I think like 301 because
I think you got it. Yeah, 301, you got it. I think let me see if other student has any problem doing this or not. Let me just take 1 more minute to see if other people can come up with the same answer. Then we'll show how it can be done. Okay, time arrived. So Xinlai, I think you get it right. So can you try to show how you get 301?
because 76 can be divided by 5 to the power of 3 times.
Yes.
So 76 is just like 3 times 5 to the power of 2.
Yes, you're right.
5 to the power of 1 plus 1 times 5 to the power of 0, and that's it.
You got it right, perfectly right. Yeah, you actually use the second method. So basically that's great. Let me just use the first method trying to, so there are 2 ways doing it. So 76, if we use the first method repeatedly, divide by 5. So why we do this is actually 1 5 is 5, so 26. Then 5 multiply 5 equal to 25. Remainder is 1. So basically 1 goes to the last digit. So this is the 5 to the 0. Then we got 15, and 15 divided by 5 equal to 3, and the remainder is 0. So remainder 0 goes to the second position, 5 to the first, 0. Then 3 is already less than 5. So 3 quotient can go to the next position. That's 3 and 5 to square. So basically that will getting the same answer. And so basically there are 2 ways of doing it. And I think, you know, you need to master both way, very important. And I think, you know, this class, whatever take away from it, you know, both method, you need to know it. And so I explain it in the, I explain this, feel it in detail in those 2 explanations. If you have question, then you can review the review my explanation in the video. I'm going to upload it later on. after the class finish. So basically that's quite important. And then let's try to go for the, yeah, so go for problem 8.9, trying to convert 1B7 base 12 to base 8. So basically, it's very difficult to convert base 12 directly to base 8. So we're going to convert this to the decimal first. So we use the decimals and convert this to decimals. So it's a two-step way to do it. And so this one is actually quite easy because it's just one. This is the ones, this is the tens, this is hundreds. Hundreds position basically is 1 multiply. And because it's base 12, so it's going to be 12 square. So that's, and then plus B. B usually, you will confuse how it works. Then you will trying to do this problem by, counting it up. So we know 9 is equivalent to 9, this is 10, base 10, base 12. Then 10 in the base 10, it's going to be base 12 will be A. So that's base 12A. Then 11 in base 10 will be 12B. So basically we are dealing with 11. So B, because B is mapping to 11. So basically 11 multiplied 12. So that's how you calculate this. And we plus 7 multiplied 12 to the 0. So basically that's the way you expand it in decimal format. And this is going to be 144. This is going to be plus 132. This is going to be plus just 7. So basically, when we adding them up, when we add first to this, going to be 6, 7, 2 plus 7, 283. So 283 is the decimal conversion from 1B7 12 base. And then we just going to be convert to base 8. To convert this to base 8, we just can use repeatedly division. So 283 divided by 8, going to be 24, 43, 40, remainder 3. So 3 goes to the 8 to the 0 position. Then 35 going to be doing the next level division. 8, so remainder 3. So 3 again, 8 to the first position. Then we actually got 4. So 4 is actually less than 8. There's no need to do further division. It can go directly to this position. So 433, that's a square. So 8, 4, 3, 3, base 8. That is what we get for this. And we can also double check by expanding it. So 8 square, basically 64. So 4 multiply 64, 256. Then this 3 multiply 8, 24. Then that's 3. So let's try to add it up to see if it works. This is actually 3 and have a 10, 13 because we're rounding up 283. So that's exactly right because those number matches. So basically, my answer is 433 base 8. So converting to 10 base, just use the power expansion. Going back to the 8 base, we just repeatedly division and putting the remainder. Then we can double check it with a different direction, just using the power expansion from the top. So basically, that's the way that you can solve this problem. Let me double check. I should be right. 8.9. Oh, let me close it and do it again. So this one, yeah, 4338. So basically everything is right. So basically there are several different ways of doing it. Just Xinlai, could you get rid of the text here because there's a lingering, yeah, thank you. So let's do the next problem. So the next problem is convert 1000 base 4 number to base 10. So, and so this one is actually quite easy. Let me just let you guys to do it. Let's give like 1 minute to do it. Anyone can finish the first problem, convert 1000 base 4 to base 10. Okay, so I think, oh yeah, Xinlai actually got it right. So 64, great. So this one basically, you convert it, basically this is 4 to the 0, 4 to the first, 4 to the second, 4 to the third. So you kind of can just label it 0, 1, 2, 3. So it has to be 1 multiply 4 to the third, which is 64. So this problem is extremely easy. And then portion B is what is the largest base 10 integer can be written as 3-digit base 4 integer. So this problem actually has 2 ways of doing it. So 3-digit base 4 integer, base 4, basically you have 0, 1, and 2. So basically, the largest possible, or 0, 1, 2, 3. So the largest possible 3-digit base 4 integer is actually 333 base 4. So 33 base 4, if you calculate this, basically is actually equal to 3 multiply, this is 0 position, 1 position, there's 2 positions. So 3 multiply 4 square plus 3 multiply 4 to the first plus 3 multiply 4 to the 0, which is equal to 3 multiply 16 plus 3 multiply 4 plus 3, which is equal to 48 plus 12 plus 3, which is equal to 63. So 63, if we just literally doing it, that will be the way to do it. But there's a quicker way. Why quicker? Because if we add 1, if this just add 1, it's going to be equal to 10004 base 4. So basically, we can just calculate this problem by, because we know the cascading rounding effect. By counting up by 1, we will get 1000 base 4. 100 base 4 is 64. But this number is 1 less, exactly 1 less than 1 0 0 0 base 4. So it's going to be 64 minus 1 equal to 63. So both way actually works. So we get to problem 10, and let's go to the next topic. We actually has a lot of problems to cover, but this is actually the first time we cover different number base. There are a lot of reasoning, there are a lot of explanation, and I really hope you can do a lot of homework, because this type of thing you have to practice it to be good at it. So just do a lot of homework, you will be good at it. Let's say that this problem, Will, can you try to read this problem?
Write each of the following as a binary integer. Find the relationship between binary integer and one twice as large. Explain why the relationship is all the same. So we've got A is 1 1. I mean, yeah. And then we've got B as 1 1 0.
Yes.
C as 1 1 1. I mean 1 1 0 0.
Yes, this is 1 1 0. This is 1 1 0 0.
Okay, that makes a pattern. Okay, and 5. That's no 1 0 1.
Yes.
10 is 1 0 1 0.
Yes.
And 20 is 1 0 1 0. I mean, 1 0 1 0 0.
Yes.
You get the pattern. All you have to do is just add 0 behind it, because it's an extra 2. So I'll tell you why. So like,
Very good. Very good.
You can just shift 1 0 1 1 0 0 1 1 0 1. I mean, no, 0 0 1. Whatever this number is, shift it and add 0.
You're right.
That's
You're right.
right.
Very good.
Because you can just multiply every single number by 0. I mean, no, by 2. So
Yes.
it's sort of shifting it to left one spot.
Yes. So this is very good observation, super in explanation. And so basically in base 10, if we multiply 10, you shift 1 0, basically you shift 0, you add 0. And in base 2, if you multiply 2, you shift 0, extra 0. And basically for any base n, if you multiply n, is actually just shift, digit by 1 position. And also when you multiply n square, it's shift by 2 position. Shift n to the k, you shift k position. Why? Because it's totally related to the power position value expansion. Because if imagine let's say it's a 2-digit, has 2-digit position, has value a multiply m to the square plus b multiply like m, then plus 0. So basically that's a fairly easy number. Even written in the base m, basically it became a, b, 0, n. But when you multiply m for this, basically it actually became a multiply n to the third, because square multiply n became third, and then plus b to the n multiply m square plus 0. So basically, everything shift 1 up, and then it's just going to be padding 1 0. So that's the reason behind it. So it's actually applied for any base whatever base you are doing, if you multiply it, the number by the base number, it's going to shift the position because of the power expansion nature of the number system. So let's see this one. This one is actually a difficult problem. And so Eddie, could you try to read problem 812?
Find the exponent of 2 in the prime factorization of 58 exclamation mark. Find the exponent of 3 in the prime factorization of 58 exclamation mark. Find the largest power of 12 that divides 58 exclamation mark. If 58 exclamation mark were written as sums of base 12 digit bundles, what would be the exponent of the smallest digit bundle with the non-zero coefficient? And how many zeros is the base 10 numeral 58 exclamation mark and when written in base 12?
Thank you. So this is actually a difficult problem. First one is actually, we already learned it. So this one is that find the exponent of 2 in the prime factorization of 58 factorial. 58 factorial is just 58 multiply 57 multiply 56, then all the way to 55 multiply 2, or 4 multiply 3 multiply 2 multiply 1, something like that. So basically, to find the exponent of 2, for all the even number, we have a single power of 2. So basically 58 divided by 2, we have 29 of, so every other number we have a factor of 2. Then we have to divide by 29 again with 2. Because every 4 position, like, 4 has 2 to the second power. So every interval 4, it's going to have extra 2 power. So 29 divided by 2 equal to 14, and remainder is 1. And the remainder does not matter. So basically it's at just 29 plus 14. 14 is where you come from every 4 interval. Then we 14 need to divide by 2 again, because that's going to be every 8 interval. That's going to be 7. So basically we have 7 of every 8 interval. Then we 7 need to divide by 2 again. That's going to be 3. So every 16 interval. And so then we will divide by 3 by 2. And we got 1. So this is 3 and remainder 1, and this is 2 and remainder 1. So basically that's 1, 3. This will be adding up to our, total of the power. So basically, we actually adding it up, we will get, this is 10, this is another 10, this is 4. So double 10, we got a 2. 2 plus 2, so 54. So 54 is the index we can get for 2. Then we trying to get 3. Let me change a different color pen. And 3, basically we 58 divided by 3. So we have 19. Every 3 interval, you got a 3 factor. 19 divided by 3. So 6 is the number. 6 divided by 3, that's going to be 2. Remainder 0, so nothing to add anymore. So basically that's 2. So that's 8. 8 plus 9 equals 7, so 27. So basically, for the exponent of 3, I have 27 as power. Then it's trying to find the largest power of 12 that divide 58. So 12 basically equal to, so 12 basically equal 2 square multiply 3. So basically, because this number has the factor of 2 to the 54 multiply 3 to the 27. So basically, if we trying to make square, so it's actually 2 square to the 27 multiply 3 to the 27. So basically, we can combine the base. 2 square multiply 3, 27. So basically, we have largest power is actually 27 for 12, because between the 54.2 index and the 27.3 index, we can squeeze out 27 of the 12 power. So problem D is that if 58 factorial were written as the sum of base 12 digit bundles, what would be the exponent of the smallest digital bundle with a non-zero coefficient? So basically, if it is a 12 based, basically it has it's some number, basically 12 to the 27th multiply a number, because it's evenly divisible by 12 to the 27th. So basically, let's say that this is x multiply. So the x, it wouldn't have any extra 12 power because it simply wouldn't exist. And so compare with, for example, if I have 1 multiply 10 to the 6, and basically, it's actually on the 7th position, because this is actually 1 million. 1, 2, 3, 4, 5, 6. So 6 zeros, and on the 7th position, it's going to have it. So it's asking that what will be the exponent of the smallest digital bundle with non-zero. So this is 27. I think it would be 27, because at 20, it's x multiplied 27. So basically it's 27. So this problem is 27, straightforward. How many zero does the base 10 number and written in how many zeros? How many zeros? That's going to be 27 zeros, because if base 10 basically, how many zero? Because we written in base 12, so we need to count zeros in the base. So these are the D and E is 27. Let's try to check the answer. Yeah, you will end with exactly 27 zeros, and this is the largest power that divide, and so basically 27 is the position you're looking for. So let's go for one more, because I don't think we have the time to finish everyone, but we go one extra, should be fine. And this time is that we're going to write 2, 6, 7, 1 to the 9th as a sum of base 9-digit bundle. So basically, this problem is actually not difficult. It's just power value expansion. And this is 0. You write position value here. This is 0 position, 1 position, 2, and 3. So 3 position. So 2 multiply 9 to the 3 because 9 is the base, plus 6 multiply 9 square, plus 7 multiply 9 to the first, plus 1 multiply 9 to the zeros. So that's the way that we're going to write as 9 the bundle. Then rewrite each power of 9 in the answer to form a power 3. Because power 9 and the power 3 has a special relationship. 9 is equal to 3 squared. So let's try to rewrite this into the 3 power. So this is actually 2 multiply 3 squared cube plus 6 multiply 3 square plus 7 multiply 3 square to the first plus just 1 because this one is actually the last digit is 1. 9 to the 0 is 1. So basically we can rewrite it into this way. And here basically, I can actually, this is 2 multiply 3 equal to 6. So it's actually 2 multiply 3 to the 6. Then plus this is 6. 6 multiply, this is 3 square going to be the fourth. Then plus this is 7 multiply 3 square plus 1. And we're going to rewrite this form into a base 3 bundle. Base 3 bundle, then we can convert this into 3 base 3 number. And this is already in the perfect because base 3 bundle, because it's actually this number coefficient is less than 3. So it's legit base 3 number, base 3 digit. So this is 3 to the 6. And we can factor out 1, 3 here because 2 multiply 3 equal to 6. So we can plus 2 multiply 3 to the 5th because you can factor out 1, 3. That 3 will multiply with 3 to the 4th. That will add up the index to 5. Then we can add 7 is greater than 2 because base 3 number cannot have anything, greater than 2. So basically, we need to convert 7 into the 3 legit number. So 7 is actually equal to 2 multiply 3 plus 1 because that's 6 plus 1. So 2 multiply 3 plus 1 multiply 3 square. Then basically it's going to be 2 multiply 3 cube. Then plus 3 square. So basically I can rewrite this into 2 multiply 3 cube plus 3 square plus 1. Then basically, I can rewrite this into the, base 3 number. So this is 3 to the 0. So 3 to the 0, that's 1. Then 3 to the first is nothing. So that's 0. 3 squared. So this is 0, 1, 2. Power 2, you have 1 because 3 squared is just equal to 1 multiply 3 square. Then this is third position, 3. That's going to have a 2 here. 4 is empty. For empty, you got 0. 2 multiply 3 to the 5th. So that's going to be 5. 5th position got a 2. And the 6th position going to be 2 also. So that's actually the number we're going to get from this conversion. And this is just, using the power expansion. But the power expansion actually, because you will notice that, for example, this 0, 1 is actually mapping to 1, and 2, 1 is actually mapping to 6, or mapping to 7, and 2, 0 is mapping up to 6. So basically, and 2 is mapping up to 2. So basically, it has for every length 2 section of the 9-digit number, you can just directly convert to the 3-digit. Then you can finish this conversion because of the splitting position, splitting property of the 9 power versus 3 power. So let me use the orange color, try to explain it. We can build a map between the number 3, 9 base number and the 3 base number. So numbers, base 9 number, you altogether have like 9 digit. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then convert to 3, it's actually 0, 0 for the base 3, and 0, 1 for the base 3, 0, 2, and 3 is 1, 0, 4 is 1, 1, 5 is 1, 2, 6 is 2, 0, 7 is 2, 1, and 8, and 8 is the last digit. Base 9 do not have a 9, and 8 is actually 2, 2. So basically, just based on this map, we are able to convert this directly. So this is that. Let me show how to do that. So for one map to 0, 1, so we need both 0 and 1. So basically, because every 2 position value on the base 3 is actually corresponding to 1 position value on the base 9. So that's how you should map. And 7 map to 2, 1. And then next 6 is mapped to 2, 0. And 2 is mapped to 0, 2, because 0, 2 is already at the dead leading number, so you don't have 2. So it's actually just 2. So basically, compare this to this, actually identical. This is 2, 2, 0, 2, 2, 0, 2, 1, 0, 1. So basically, this is actually a much quicker way if you use every 9 digit is related to 2 of the 3 base 3 digits. So that's the way we convert it. Okay, I think that's all for today. And we still have a few leftover problems going to explain next time. Have a nice one. Bye-bye.
Thank you.
Thank you.
Bye.